time signal may be represented. I mean, the representation could be such that the independent variable, the source, is discrete itself. Okay, what it means is that you don't in all the times you don't have to discretize a continuous time signal to produce a discrete time signal or a sequence. You can have a data, for example, you should consider stock market data, and if you consider the values of the stocks at each successive weeks, the source is discrete in nature. The nature of the source is discrete. Okay, it's not discretized. It's not being produced by a certain A to D converter, for example. Okay, this phenomena is inherently discrete, right? So X of n may represent a phenomena for which the independent variable is inherently discrete. So signals such as demographic data, for example, data of population, okay, or an average budget of a family, monthly budget of a family is discrete. The data is discrete itself. On the other hand, a very important class of discrete time signals arises from the sampling of continuous time signals. So in this case, the discrete time signal X of n represent successive samples of underlying phenomena for which the independent variable is continuous. For example, for a speed signal, as I've said, for example, if xt, or okay, if we consider the pressure fluctuations as we've seen earlier, for a microphone signal that is translated those pressure fluctuations into corresponding electrical signals, you might want to pass them through an A to D converter, okay, to produce let's say another signal, call it P of n, which is a digital signal. Okay, P of n is a digital signal because it has been discretized. Not only the time, but the amplitude has also been discretized. Okay, let's say it's an 8-bit converter, and there are 2 to the power 8 possible levels that the amplitudes can take from. So again, these amplitude levels are they are going to take the values from a finite set of values, finite set of possible values. So this is a digital data. Okay, and then you can go ahead and you can store this data on a on a piece of magnetic media or a machine on a hard drive. Okay, or you can process this digitally. Okay, for example, this signal can be processed by a DSP processor. Okay, and this DSP processor could it can do the task like addition, delay, and multiplication to produce another set of data. Let's call this processed data as Z of n. Okay, Z of n could be different from P of n, right? It could be, for example, a filtered data. You have to, for example, remove the high frequency noise. You might want to implement a low pass digital filter. Okay, so you might want to do this in a computer, and then again you after processing you pass this through a DAC, digital to analog converter. Okay, and if there are any high frequency fluctuations, you might want to add an analog low pass filter, and then you can listen to the sound, you can listen to the process sound, call it let's say C of t. Okay, so C of t at the end and P of t are both analog signals. This analog signals has been processed digitally by means of DSP processor, right? And for that you have to consider the processes of sampling and digitization as happens in ADC. Okay, and this signal, once it is stored, it can be processed digitally by machines, okay, by digital machines like computers having softwares which can process the data. They can store them, okay, they can relay them to, for example, if it's a piece of speech or music, it can be filtered, the quality of sound can be enhanced, and then it sends the data back to you as sound through digital to analog conversion. Okay, so the signal is sent back to the sound card from which the music is being played, and you get back an analog signal, which is a better version of the original analog signal, only that it has been processed digitally. Okay, there are certain advantages why we do this digitally, and now after 70s there has been a boom in IC technology, for example, which has made all this possible at a drastically reduced prices. You see, we can store the digital signals. Okay, there is no way of storing analog signals. The world is analog, but machines they can process the signals digitally, right? So you can store the signals for as long as you require, and there's no requirement of calibration in softwares, let's say. So, for example, if you have to do analog signal processing, you might have to calibrate instruments, right? So there are certain advantages associated. You have more flexibility, right, in digital signal processing. So digital signal processing got a lot of attention in early 70s, and for now, uh, DSP is most favored choice of processing the signals, right? So no matter what the source of data is, I mean, the source of data I mean, it could either come from a digital, it might not be a continuous time signal which has been sampled and discretized to produce a discrete time sequence. It could be the source of data could be, for example, stock market data or demographic data with population data, which is inherently discrete in nature. Okay. So, but however, the signal x of n is defined only for integral values of n, only integer values of n. Okay. Uh, so x of n, as I've already mentioned before, is it's going to take only integer values. Okay, not the continuum. Another important classifications of signal is in terms of energy and power. You see, most of the signals that we encounter are related to the physical phenomena. Okay, so in many, but not all the applications, signals that we consider are directly related to physical quantities, capturing power and energy in physical system. For example, as an example, if Vt and It are the voltages and the current across a resistor, an electrical system, with resistance R, then the instantaneous power is given by the product of Vt and It, right? And then since I is given by Vt over R, you can write this as V square over R. So the total energy can be found out by integrating the power with respect to time over the interval t1 to t2, right? And this is just energy in a given interval t1 to t2. But if you are interested in evaluating the energy of such physical system for the entire time, then you have to evaluate this integral as a limit that t tends to infinity, right? So this is just the description of how we evaluate the energy corresponding to those signals Vt and It. Similarly, you can find the average power over this interval. Average power is just division. I mean, you have this is the energy. Okay, just take the average over the time period over which you're evaluating the energy, and that's given by the instant t2 to minus t1. Okay, so t2 minus t1 is the instant. So it's again the average power is evaluated by dividing the energy by the given time instant. Okay, so it is common and worthwhile convention to use similar terminology for power and energy for continuous time signal or any discrete time signal x of n. To consider signals that may take on complex values, the total energy in this case over the time interval t1 to t2 in a continuous time signal is defined as, for example, if your xt is a complex value signal, it takes complex values. Energy and power cannot be complex, right? For example, energy has to be real, okay, has to be real and finite. If the energy is infinite, for example, if the signal does not converges, then this is not a finite energy signal, right? I mean, there could be cases for which the signal does not converge, for which the integral does not converge, and therefore those are not finite energy signals, fine. But what we're trying to imply over here is that if the signal is complex, then you might have to take the amplitude. Okay, so this magnitude represents denotes the magnitude of possibly complex numbers, and take the square of that. Okay, because a volt square normalized over a unity ohm resistance is the power, right? And if you have to integrate this with respect to time, it becomes energy, right? So it could be complex. If you're dealing with the complex signals, you have to take the magnitude squared. Okay, this is in general. So the time average power is again obtained by dividing the above equation by the length t2 minus t1. That's the instant time for which we are considering the energy. Similarly, the total energy in the discrete time signal x of n over the interval, since x of n is a sequence, we just have to add up the magnitude squared samples. Okay, the the magnitude of the sample squared. So just add them over the instance n1 to n2, and gives you the power in the discrete time sequence over the given interval. So if you divide this by the number of points, n2 minus n1 plus 1, this yields the average power over the interval. Okay. So for example, if n1 is a negative quantity and n2 is a positive integer, there's a 0 in between. Okay. So for example, if you have considering the length from, let's say, -1 to 1, then the total length of the sequence is 3. There are 3 samples, right? This is the 0 over here. So this makes the length, for example, if this is 1, and the length in general becomes, if this is n2, this is n1, so you can see this. The difference, this 1 corresponds to the 0 sample over here in between. You have to consider this as well. Okay. All right. So furthermore, in many cases, we'll be interested in examining the power and energy in signals over an infinite time interval. For an infinite time interval, or for infinite length of the sequence, n is the length of the sequence. So in these cases, we define the total energy as the limit of energy, power equations. The time interval increases without the bound. For example, the total energy is given by extending this period, allowing the period t to go to infinity, gives the total energy of the physical phenomena that is being captured by the signal xt, which might in general be complex. So you have to take the magnitude squared of that, and then you have to integrate with respect to time. Okay, so this is, for example, this is the power. You integrate with respect to time, allow the time t goes to infinity. This gives you E infinity. This is the energy contained in the signal xt over the entire duration. Similarly, in discrete time, you have the summation, and you allow the length of the samples go to infinity. Note that for some signals, the above integral or summation over infinite interval or the discrete time index n might not converge. In that case, those are not the energy signals. Okay, those are not infinite. Those are not finite energy signals. For example, if xt or x of n equals a non-zero or constant value of value for all time, such signals have infinite energy, while the signals where ex is less than infinity have a finite energy. So if this is less than infinity, if the integral converges or if the summation converges, then the discrete time or continuous time signals are finite energy signals. They're finite energy signals. If the integral does not converges, then they can be power signals, okay, or they could not be. For example, if you have a constant over here, right? If xt is a constant, then integrating a constant over an infinite duration is infinite, right? So it's not an energy signal. However, if the energy, but on the other hand, let's say if energy is finite and you're considering this energy from the xt only exists, even if it's a constant, let's say you have a signal like this. It exists from 0 to 1, okay, having magnitude of 1. This is my xt, right? Again, you see the magnitude squared of xt is unity, right? So it doesn't matter. And the magnitude squared is also unity. So that means the energy of the signal, Ex, is 1 dot dt, and you have to integrate this from 0 to 1, which is what? Which is 1, right? So the energy is 1. This is 1. So this is purely an energy signal. Okay. What is the power? The power similarly can be defined as, if you allow the t to go to infinity. Okay. So that is for the limit t goes to infinity, and then you have to take the average, and then there's energy of the signal Ex. Even if Ex is finite, the power is 0. So for finite energy signals, their average power is 0. If the because since the power is defined as the average of the energy, and this if you allow the just considering a very large interval over which the averaging is going to be taken, if this t is going to infinity, then the length of the averaging time interval is large, your power is 0. Your power is 0. Okay, so for finite energy signals, the average power is 0. The average power is 0. Similarly, for finite power signals, the energy is infinite. Okay, so let's consider why is that. So in analogous fashion, you can define the time average power over an infinite interval as like this. This is again the definition for the discrete time signal over the length 2n plus 1 in continuous time and discrete time respectively. So with these definitions, we can identify three important classes of signals. The first of these is a class of signals with finite total energy. Okay, for example, this is a finite energy signal. Okay, those signals for which the energy is finite are finite energy signals. Such a signal must have a zero average power, since in the continuous time case, for example, you see, we have seen this. If you consider, if you allow t to go to infinity, okay, the average is being taken over an infinite interval. Okay, let's say this is infinity. Then taking the average, so 1 over infinity is 0, right? So the power is 0. The total power is 0. So the average power has to be 0. So this, you see, this is how the energy is defined. So this is your Ex over 2t, and if t is very large, the P infinite is 0. Okay, the average power is 0. The second class of signals are those with finite average power, and for those finite average power, if P infinite is finite, then it necessarily implies that Ex is infinity. And this of course makes sense, since if there is non-zero average uh, energy per unit time, it means non-zero power, then integrating or summing this over an infinite interval yields an infinite amount of energy, right? So if the power is finite, as given by P infinity greater than 0, integrating or summing this quantity over an infinite interval without taking average gives you infinite energy. For example, periodic signals, okay, which the pattern for which is continuously varying over a certain period and is continuous forever, the energy contained is infinite, right? The energy contained is infinite. However, their average power in one period is finite. The average power in one period is finite. Even the average energy, not the average energy, the average power is finite if you consider one cycle, right? But the energy in one cycle could be finite, but if you have to consider the energy for the entire existence of the signal, it's infinite, right? The periodic signal is one example of this second class of signals for which the average power is finite, but energy is infinite. For example, the constant x of n equal to 4 has infinite energy, right? I mean, if x of n is equal to 4, then you are just summing up 16, for example, or a very large for the energy for such a signal, infinity, for a discrete time signal, will be just a summation x of n, since this is a, okay, let's take the magnitude squared. This is 16, and n is going to vary from minus infinity to plus infinity, right? And this is, you see, this is 16 times infinite, right? So you're adding 16, so this is again infinity, right? So the energy, it's not a finite energy signal, okay? This has infinite energy, which means the average power is going to be finite. Why? Because if you're going to consider an length 1 over 2n plus 1, which is very large. So if if I make the, okay, its definition, P infinity is equal to 1 over 2n plus 1, where n is a very large sample, you allow n to go to infinity, and then you sum it up, you are going to sum basically 16 over length n from minus n to plus n, and this will be equal to 16 times 2n plus 1 over 2n plus 1. And guess what? This simply cancels out, right? I mean, the length is 2n plus 1, and the summation is as such that you have to sum 16 2n plus 1 times, so this cancels, leaving you a finite average power for which the energy was infinite. So this class of signals have average power that is finite, but energy is infinite. Okay, Then there's another third class. There's yet another class, third class, which not third class, but I mean it's just the way the nomenclature has gone. So first you have finite energy signals. Then second is that you have uh, finite power signals for which the energy is infinite. For energy signals, the power is zero. Um, you get another class in which you neither have P infinite or Ex as finite. So neither the power is finite, neither the energy is finite, and a simple example is signal xt equal to t, right? So if this is not convergent, the average power is not converging, or even your E infinity is not converging, then we say the signal neither they have a finite energy, neither they have a finite power. Okay, and one example is xt is equal to t. Okay, and you can carry out the algebra to show that such signals they do exist. Okay, that's all.